Let us discuss some more theory. You come across ammeter, voltmeter, galvanometer. How exactly do these things work? I am talking in the context of DC. In the context of DC, direct current, which we are discussing, alternating current means current changes direction repeatedly. In DC discussion, current does not change direction repeatedly. That's what we are discussing right now. In that context, there is some magnetic field inside that device, whatever it is, ammeter, voltmeter or galvanometer. And there's a coil, and when current passes through that coil, magnetic field applies torque, that is forces which produce rotation. So the coil rotates and you notice that deflection, right? So the deflection produced is proportional to the current. The deflection theta produced is proportional to the current that passes through the coil. That's a basic principle. Whether it is galvanometer, ammeter or voltmeter, the principle is the same in the three cases. In case of galvanometer, the needle by default is at the middle, and depending on which direction current is flowing, it can go right or it can go to the left, right? That's about galvanometer. In case of ammeter, it's one-way traffic. When there is no current, needle is at absolute left, it's showing 0, and when the current is there, it turns clockwise more and more and more and more and more. And likewise for voltmeter, when the potential difference is more and more and more, it will show higher and higher and higher readings. Ammeter measures the current. That means if you want to know current through this wire, then you will have to connect to an ammeter like this. Notice that plus sign. Ammeter has to be connected properly with proper polarity. You can't let the current pass in opposite direction for ammeter. The side from where current enters, that's the positive side of the ammeter, right? So current must enter like that, and what you may not see, of course you won't see it, is the coil inside. So this current is actually going through some coil inside it. And when the current passes through that coil, which is in magnetic field, it will rotate. And in case of voltmeter, if you want to know potential difference across the 2 points, these 2 points can be part of some big circuit. So imagine some big circuit and you just want potential difference across these 2 points. You will connect the voltmeter like this. Voltmeter always connected across the 2 points. So that's a big difference how you connect an ammeter and how you connect a voltmeter. Voltmeter always is connected across the 2 points across which you are wanting to measure the potential difference. Ammeter means current should pass through it, that you are wanting to measure. That whole current you are wanting to measure should pass through it. Okay? Galvanometer means left, right, both deflections are possible. And inside, if you see, for any of these, inside is quite similar. Principle-wise, it's similar. Now, a good measuring instrument is that instrument which does not change the characteristics of the circuit. A good measuring instrument's job is to only measure. It should not disturb the circuit. So if you have some big circuit and through some resistor, in reality 5 ampere current is flowing, suppose. Then when you connect that ammeter to measure that 5 ampere, then 5 ampere should not become 4.5 ampere. A measuring instrument good measuring instrument should never change the characteristics of the circuit. So if in reality the current is 5 amperes through some resistor and I want to know how much is it, and I put an ammeter there to do that job and it tells me 4.5 amperes, it's not really a good thing. You do not want your instrument to change the characteristics of the circuit. I want to measure potential difference across 2 points, and suppose it is in reality 50 volts in reality. Now I connect my voltmeter there, and the moment I connect it, voltmeter disturbs the circuit, and that 50 becomes 40. That's not good. A good measuring instrument should not change the characteristics of the circuit. So, if you are using ammeter to measure the current through this, you don't want ammeter to disturb the circuit. So ideally, ammeter should have zero resistance. If ammeter has zero resistance, then whatever current was flowing earlier, exactly the same current will flow now also. If ammeter has zero resistance, then it will work very well. But in reality, practically speaking, that's not possible. How can you have a coil which has zero resistance, practically speaking? You can have as small as possible. So you try to reach there as small as possible. You try to reach zero. You try to reach as small as possible. Now supposing I give you the coil of this whatever you call it, galvanometer, whatever this thing is. I give you its coil and I tell you that I want to use it as ammeter. I want to use it as ammeter. And because of that, I want to reduce its resistance. Should I connect another resistor in parallel or in series? I mean, parallel means here. Should I connect in parallel like this, or should I connect in series? That's right. So, because these instruments work on the same principle, then it should be possible to convert one to the other, right? So, if you are wanting to use galvanometer as ammeter, then you should try to make sure that the resistance is as small as possible. Resistance is as small as possible. So, you would connect something in parallel for ammeter. Now, for voltmeter, the story is exactly the opposite. Voltmeter means, suppose some resistor was connected here, and we of course want to measure potential difference across 2 points. The moment voltmeter is connected, some current was going through this, maybe some wire was connected here. All of this current was going through that. All of it earlier. The moment voltmeter was connected, some part of that current must go through the voltmeter. Now, if 5 was coming here, 5 was going there. Now, if voltmeter takes 0.5, then 4.5 will go here. But then the potential difference across 2 points would be obviously changed. From Ohm's law, V is equal to IR. Now 4.5 R is clearly different from 5 R. Characteristics of the circuit are changed. You don't want that to happen. So ideally speaking, your voltmeter should take nothing. 0 ampere out of 5 ampere. All 5 amperes should continue to go through that resistor and you get exactly the same answer. But practically speaking, can a voltmeter work like a magic? It takes no current and coil rotates in magnetic field. How can coil inside the voltmeter rotate in magnetic field if there is no current passing through it? Magnetic field will apply force to current. If current is not flowing, how can there be any force? If there can be no force, how can there be torque? That means voltmeter is going to eat some current. You just cannot help it. But you can minimize the damage. Now, ideal voltmeter means infinite resistance. It takes no current. Ideal voltmeter is only theoretical. It will take absolutely no current. So we say ideal voltmeter has infinite resistance, takes no current. Ideal ammeter has 0 resistance. Whatever current was passing earlier, same will pass now. Practically speaking, you cannot have deflection without some current. So, and also ideally speaking, I discussed. Realistically speaking, you can try to minimize this current. You can try to minimize this current. That means take as high resistance as possible here. Take as high resistance as possible. So if you have some galvanometer, you want to use it as a voltmeter, you try to make its resistance as high as you can. You can't really, you won't like to open it and fiddle with the coil. That is fitted in some factory, coil, etc. So you don't fiddle with the coil, but you can connect a resistor in series. So supposing you have something called galvanometer, factory made, coil is fitted, etc. But you are seeing the 2 points and you will connect a resistor of your choice here. So for you, effectively speaking, your voltmeter is across these 2 points. Your voltmeter is across these 2 points. And not these 2 points. Right? So I hope these ideas are clear. Ideal ammeter, ideal voltmeter, series connection, parallel connection. A practical ammeter, what should be done for practical ammeter, for practical voltmeter, what should be done. Any questions you have in theory, then let me know, or I will take problems. The purpose of this experiment is to find the EMF of the battery and the internal resistance of the battery. First, switch S was kept open, just like this. Open switch means it is not connecting, just like this. That's open switch. And when the switch is open, then the voltmeter reads 1.52 volts. Now the switch is closed and the voltmeter and ammeter readings are recorded. Voltmeter showed 1.45 volts, ammeter showed 1.0 amperes. The voltmeter has very high resistance. That means it is ideal voltmeter. Ammeter has some resistance. That means it is not an ideal ammeter. It is not an ideal ammeter. This is an ideal voltmeter. From this information, one has to find the EMF and the internal resistance. I hope the question is clear. Any clarification about the question, let me know. Fine. Let's make equations now. When it is closed, this is very high resistance. Current won't flow through this. It is closed, right? It is very high resistance means current won't flow through this also. So, whatever is the reading, it is the reading without current. It is the reading without current. And the reading without current is the true EMF. That means EMF is 1.52 volts. Right? When switch is closed, then current cannot flow through this. Current will flow like this. And that current is 1 ampere. Instead of I, let me call it just 1. Now, the voltmeter reading is the potential difference across these 2 points. Okay, so let's start from B, go towards A. Or let me use this language that potential difference across A and B is potential difference across this plus potential difference across that, right? So that would be, if we call it C, then it would be VA minus VC plus VC minus VB. VA minus VC is plus E, and since current is flowing like this, it means positive of the resistor is this, positive side of the resistor is this, negative side of the resistor is this. Okay, that means C is at a lower potential. C is at a lower potential. So VC minus VB is going to be minus IR. Minus I, then small r. And normally speaking, when a battery is used like this, then voltage across the battery is E minus IR. That's a very quick way to get it, E minus IR. And E is 1.52. into small r, and VA minus VB is 1.45. Can you calculate small r from this? That's right. So that's it. If you have any questions regarding this discussion, then let me know or we proceed further. EMF is given 4.3 volt. Internal resistance is given 1 ohm. External resistance is given 50 ohms. Coil of emitters, or I should say the total emitter resistance. Total emitter resistance is 2 ohms and the voltmeter resistance is 200 ohms. Okay, now questions are, what are the readings of the two measuring instruments in the current situation? In the current situation, when the switch is on the left side, then what are the readings of the two instruments? That's going to be very easy. You see, this part is simply not connected anywhere, so you can simply cut this part mentally. Now we want current, we want potential difference across these 2 points. I think we go for Kirchhoff's law approach. Okay, so let's take this current to be I and this current to be I dash. I comes, I dash goes, so this one would be I minus I dash. Okay. Let's start from here. We have got several choices as far as loops are concerned. Let's go for the top loop and the lower loop. So for the top loop, let's go from here. Current is like this. That means this should be positive. Plus IR. Then we reach negative. That means minus E. Then current is this direction, means this should be positive. Plus I minus I dash R. Ammeter has resistance. I is back. This is all I. This is all I. So through ammeter it will be I, and this is the resistor RA. Entering it means it is plus. So plus times I times RA. Back home, 0. Now, consider this small loop. Suppose we start from here and go like this, going in the opposite direction of current. So it's going to be from negative to positive. Minus I dash R. Going in the direction of the current, this is a coil inside, means resistor inside. So it could be the positive end. Positive end means plus I dash RV. Looks like we are back home. That's it, 0. You have all the numbers written here. Can you quickly solve as quickly as possible for I and I dash? I and I dash. Okay, you are getting 0.1, 0.02. Assuming these are correct, the reading of ammeter would be how much? 0.1. And reading of voltmeter would be how much? I minus I dash. Voltmeter is measuring potential difference across R, capital R, right? So total current I minus I dash multiplied by 50. Please calculate this also. See how much you get for that. It should be 4. Just recheck your calculation. It should be 0.1 ampere and 4 volts. Now in this discussion, if you have any question, then let me know up to this point. Look at the figures and imagine that the switch is thrown to the other side, right? In that situation, you have to find out the readings of the two instruments, and this is your assignment question. We are continuing further, but I am giving the assignment question right now. Okay? Now, proceeding further. Practically speaking, a measuring instrument can change the characteristics of a circuit, which is not good, but it's possible, and this question is based on that. Actually, the choice of measuring instrument is important. So if you are performing some experiment, then you have to be careful with the choice of your voltmeter, ammeter, etc. In this particular problem, the choice does not look good. Voltmeter has a resistance of 400 ohms, and look at these resistances, 100 ohm, 200 ohm. Comparative resistances should not be there. 100 ohm versus 400 ohm. 400 ohm is not too big for 100 ohm. So when the current splitting will take place here, it's going to be quite a bit for this part. The choice of instrument should be such that with respect to 100 ohms, this number should have been big. 1 kilo ohm would have been better, 10 kilo ohm would have been even better, but 400 ohm with respect to 100 ohm does not look like a great idea. So let's see what happens due to that. The purpose, of course, is to measure potential difference across 100. That's why we have connected it. So, first question is, what is the voltmeter reading? And second question is, without voltmeters, what is the true potential difference across 100 ohm resistor, the true potential difference across 100 ohm resistance. Okay. So right now this is 400 ohm, and these two are in parallel, 100 and 400. That means 100 into 400 divided by 100 plus 400. How much is that? 80 ohm. 80 ohm in series with 200 ohm. 280 ohm. And how much current total battery will supply? 280 ohm. In fact, calculation is not required. We can just write 84 divided by 280. So that current is going to enter this region, and that current will split between these two. But actually we want voltmeter readings, so why worry about current splitting? Why not just say that these two are equivalent to 80 ohm, and just imagine 80 ohm here. 80 ohm is taking this much current. 80 ohm is taking that much current, so how much will be the potential drop? That's it, as simple as that. That will be the potential difference across 80 ohm. That will be the potential difference across 100 ohm. That will be the potential difference across this voltmeter. All same. Just calculate this. This should be your answer. That's right. 24 volts. So that's the voltmeter reading. Any questions up to this point? If you have, let me know. Or I move on to the truth part, the real potential difference without voltmeter. Okay, so let's discuss the real thing. I mean the truth without voltmeter. Cut it. Cut it. 84 volts across two resistors in series. We can use that quick series potential drop formula. 100 upon 100 plus 200 multiplied by 84 would be the answer. That means 1/3 of 84. 1/3 of 84 is 28. 28. Versus 24, so error of 4. Out of 28, 10% is 2.8. 10% is 2.8. So we are talking something like 14-15% error. I mean change. 14-15% change we are talking about. That's substantial change. It is due to that wrong choice of this voltmeter. If experimenter had gone for voltmeter with higher internal resistance, much higher than 100, things would have been different. Well, if coil has deflected to the maximum extent, you can't cross that limit. That's the maximum. So supposing this is a range by which needle can move. That's it. That's the end. And coil is getting that much torque at 10 milliamperes. So that's the limit. You can't let more than 10 milliampere current pass through the coil. So you see that coil has very small resistance, just 25 ohms. And because intention is to use this as voltmeter, a series resistor is connected, 575 ohms. So totally it makes it 600 ohms. Okay. That capital R is part of the voltmeter. So we say voltmeter is connected across 2 points. So those 2 points will be like these. Capital R is part of the voltmeter. So voltmeter will measure potential difference across these 2 points. The maximum permissible current is 10 milliamperes through that coil. So because capital R is in series with the coil, 10 milliampere will flow through that also. 10 milliamperes, 600 ohms. It should be a very simple question to answer. What is VAB? Can you check for the decimal errors? Multiple of 10. Yes, it is 6 volts. One milliampere. Shunt is the same resistance. Shunt is this. We are talking about ammeters. The parallel resistance that you connect across ammeter, that is a shunt resistance, parallel resistance connected. Now, coil can take only 1 milliampere, but you want to measure up to 1 milliampere it can do, but you want to measure up to 2. Okay. So your coil can take only 1, right? But you want input to be up to 2. Input to be up to 2. This is the shunt resistor. This is the coil resistance. Ammeter totally should be able to measure 2, up to 2. Right? Now, shunt has this purpose also. You would see different types of ammeters. Some ammeters can measure up to this, some ammeters can be measured to that. You can convert the scale by choosing appropriate shunt. You can convert the scale. The scale that is made, that scaling can be changed by looking at this. If you want to measure 2 ampere current, choose capital R such that 1 milliampere only goes through it, right? And it deflects completely, and you have written down when will it be 1 ampere, when it will be 2 ampere. Scale has been made by you. That is the calibration part. So that clearly means that 2 is the input current, 1 MA will go through this, rest will go through capital R. Ammeter is this whole system. This will be called ammeter from here to here. So you have the concept of parallel resistor, and through this 1 MA flows. That means R upon small r plus r into 2 is 1 MA. Right? And small r is 25 ohms. Small r is given to you. Can you quickly find capital R? Find out capital R. And the answer you should get is, it should be a small resistance because most of the current is going through it. Only 1 milliampere is going through this. So shunt is going to be a small resistor which takes most of the current through it. The answer is 1.25. Right side is milli. Be careful with the zeros. 10 to the power minus 2 ohms. See if you are getting it. Fine. I have already given you the assignment, I think in board number 3. Yes, part B of this question. So we stop at this point.